Next speaker is Vitaliy Yakovlev from the Academy of Science, Ukraine. Please go ahead.
Yes, okay. The theory of flexural gravity waves is rather widely developed on the basis of linear models, but much more interesting are nonlinear models. As to the mathematical point of view for nonlinear flexural gravity wave problems, the boundary conditions on a free surface have more a difficult character in comparison with the corresponding condition for linear flexural gravity waves and nonlinear gravitational waves. Surface waves in an ice field are the combination of flexible wave in an ice plate and gravity wave in water. This duality brings essential, just a minute. Yes. Essential change into a wave dispersion. Proper type oscillation prevail according to the relation between the gravity and the rigidity of the plate. Inertial forces of ice mass and elastic forces counterbalance the wave pressure and define the dynamic condition on the interface ice-water. The dynamic condition for flexible gravity waves takes rather complicated form and the detailed researching of the physical laws of propagation of these waves is very difficult. In Vorsk, Gladun, Fedosenko, generalization of the theory of nonlinear Stokes waves for the case of the flexural gravity waves is presented, and physical regularities of propagation of these waves for cases of finite and infinite fluid depths are revealed. Within such models, the solutions of soliton types describing waves which can travel with constant speed without change of the form are constructed. The most significant nonlinear effects of flexural gravity waves theory were shown in the case of long waves. There exist many mathematical models and solutions for long linear flexural gravity waves. However, the incorrect taking account of nonlinear effects leads to the wrong modeling of the studied phenomena, according to inexact conclusions concerning the existence of waves of this or that character depending on problem parameters. For example, artificial entering of preliminary plate tension determinate an existence of a discrete range of distance at which small change of one parameters leads to disappearance of a flexural gravity soliton that does not correspond to physics of the considered phenomenon. The accounting, for example, the geometrical nonlinear deflection of plate gives an additive to coefficient at the third derivative in the equation. And if speak about solution of the received equation or even about the area of existent of possible solution of various character, it cannot but influence the result. Due to this additive, it becomes possible to define the continuous area of change of parameters where exists the soliton solution of equation. The well-known model which describes the two-dimensional soliton-like solution for water waves, Kadomtsev equation is. For the first time, just a minute. For the first time, this equation was offered in work Kadomtsev, wherefore its constructor actually general ideas of nature of the physics forces iterating in this process and their mathematical description were used. In work Hierarchical Cell Illichov, where KP equation for modeling of flexural gravity and capillary waves is received. One of the main effects at this expense of which there can exist, the most interesting including soliton solution, namely the influence of an elastic plate, isn't considered as the equation deriving. Authors motivate it which that such account doesn't give a contribution to the equation. However, just the accounting of geometrical nonlinear deflection of plate leads to the generalized equation of Korteweg, which allows study soliton solution. Long flexural gravity waves. Let's consider the potential wave movement of ideal incompressible fluid of variable depth with a free surface covered with an elastic plate. Let plane coincide with undisturbed surface of fluid, and the axis is directed up. In this case, the boundary problem is described by equation 1, 2, 3, and 4. Just a minute. Which the corresponding condition on the bottom z equal minus h and the surface of contact of liquid and elastic plate, taking into account geometrical nonlinear deflection of the plate, z equal zeta z. 6, 7, 8. Here, W speed vector components, pressure in fluid, ρ2 fluid density, ρ1 H1 dE, respectively, fluid density, thickness, cylindrical rigidity, and model of elasticity of a plate. Sigma z, zeta z, phi, sigma x, sigma y, tau, deflection, function of tension, and components of tensor of tension in a medium surface of a plate, respectively. Let's design F equal H plus zeta. Integrate the equation 1, 2, and 4 over depth from minus H to zeta z, taking into account boundary condition 5, 7. After some transformation, we received equation of long wave nonlinear dispersion approximation, which describe propagation of flexural gravity waves in elastic plate on the surface on fluid of variable depth, taking into account geometrically nonlinear deflection of plate. Нет, сейчас тут я убрал. Да? Okay. Hierarchical sequence of model of long flexural gravity waves deriving of exact solution. Let's consider dynamic process of a bend of a plate without propagation of elastic waves. That gives the chance to reject inertial members. Inertia here, zeta x, zeta is components of a vector movements of a medium surface of an elastic plate. For one-dimensional case, from the movement equation, we have this having integrated the last equation over x, we obtain epsilon x equal constant, where epsilon x in median surface deformation due to geometrically nonlinear deflection. Therefore, one-dimensional case L of zeta z phi equal this. In equation 911 for nonlinear dispersive approximation of propagation of flexural gravity waves in elastic plate floating on fluid surface, after introducing the dimensional variables in this form, we obtain take the form. Here R and Q equal this. The derived model describing effects of nonlinear dispersion of fluids, terms of the order of such product alpha and beta, and also consider inertia and geometric nonlinear deflection of the plate. Keeping is the equation 15 terms of the order alpha beta and those that correspond to geometrically nonlinear deflection of a plate will receive Peregrine equation describing transformation of long waves of final but small amplitude in 16 equation. In one-dimensional case, H equal constant from equation 14-16, we will obtain the system of equation like Boussinesque, equation 17-18. Using the transformation similar with them from system 17-18, receive the equation 18, which according to the classification the Bhat-Nagar belongs to the class of the generalized Korteweg-de-Vries equation. Let's study stationary solution of the equation 19 in the form. Substituted expression 20 into 19, then integrating twice and entering new variables x and x and y of x equal is this form we get. We will look for the solution of equation 21 in the form power series. Substituting this series to the 21, equating coefficient at equal degrees x alpha, and considering tau of zeta squared equal x, we find where to answer the question about the number character of roots this equation, there is need to consider separately each option, since it is possible to show that roots in one and another cases differ only signs, respectively, intervals of keeping signs for cubic polynomials 22 as symmetric as to 0. Under certain conditions, the equation 22 can describe the periodic movement which exists between two adjacent real zeros of the function f of tau, where f of tau is not negative. Function f of tau of cubic polynomial having three roots. In word Korteweg-de-Vries, the case describing non-constant finite decisions of 22 have been studied in details. As existence of solution as existence of soliton as a decision of 22 is defined by presence of two equal roots and the cubic equation. The soliton can exist only at U equal C0. This decision was derived in work Korteweg-de-Vries. As a result, the research of possible roots of polynomial f of tau, depending on physical parameters of the model, intervals of changing of these parameters, where is generalized equated of Kadomtsev, has the solution in the form of the soliton or cnoidal wave have been defined. The soliton wave exists for epsilon x is greater than this when f of tau has three real roots, two of which are equal, and has the form of fig 1. See fig 1. The flexural gravity soliton is turned out the relation to the soliton of water, and existence of preliminary stretching in a plate is not necessary condition of its emergence. For this soliton, the propagation speed is determined and contrary to waves on water is decreases with growth of amplitude of wave. The solution representable by cnoidal function, the equation 22, allows in case of existing of three real roots for the polynomial as upcards from 23 is possible only at U less than C0. Obviously, the easiest case to construct the decision of 22 in the form of cnoidal wave is the kappa equals 0. The equation 22 at this case has the form where f of tau in this form. Using cnoidal function, we can present the solution of considered equation in the following form. we obtain that for the case of equilibrium dispersive forces considered in this model, dispersion of fluid, inertia of an ice plate, and the dispersion due to geometrically non-linear deflection of plate, kappa equal 0. The initial equation has the solution which can be put down in the form of cnoidal waves. For the accepted problem, definition due to the entered dimensionless variables from the ratio 9c squared equal 1, we can receive equality pair for flexural gravity soliton. Constructing such surface, we obtained elliptical, almost circular cone, Fig 3, which defines interrelation of the key physical parameters of the problem to dispersion and non-linearity. In the case of existence of the soliton solution for the considered equation. The Longwave nonlinear dispersive model 19, constructed in such a way and describing the propagation of flexural gravity waves in the elastic plate floating on fluid surface, is very interesting from the point of view of process physics, as the equation contain k physical parameters defining the character of its possible solutions in an explicit form. Two-dimensional flexural gravitational level. Let's just a minute. Let's consider now two-dimensional flexural gravity waves. The task about hydroelastic fluctuation of system an elastic plate ideal incompressible fluid is reduced to Laplace equation for the speed potential 26 with corresponding boundary condition on the bottom 27 and the interface ice water 28 and 29. Where we have L of zeta f 13 and formula 21 and 22. 31 is 32. Under linear indexes designed differentiation by corresponding variables, dimensionless variables entered earlier. See 13. Let's construct Longwave approximation for a system equation 2632 by means of series small parameter, not by averaging over depth as it was done in previous part 33. Substituting this series in the boundary condition at the bottom to Laplace equation and boundary condition at interface ice water after same transformation had 34. Let substitute. Just a minute. Let вот это. Вот это, да. Let substitute 33 to the remaining boundary condition and the interface ice water, and also holding only terms of order alpha and beta, we obtain 35. Replacement of variables in this form using the assumption that all follow assumption, using the follow assumption, this and this, transformation transform the last two equations to the form 36. After several transformations, the equation system 36 is reduced to the following equation. Passing to system variables x, xi, t, and designing h equal this form, we obtained. Using series for fractional degrees of h and having designed eta equal fx, we will finally obtain the generalized Kadomtsev-Peregrine equation, the 37. Thus, we received the equation describing the propagation of two-dimensional flexural gravity waves in the sea covered with ice, as well as in the generalized equation of Korteweg. In this equation, the additional term, including the third derivative eta xxx, appears that leads to existence of solutions of various type depending on relation of parameters at this derivative. To build the decision, let's to the scale replacement in equation 37 to get rid of coefficient at derivative. As a result, we can get the equation 38. To get analytical solution of such equation in general case is not possible without simplifying assumption. For example, about periodicity of the desired solution by y or x coordinate, or about the fulfillment of certain boundary condition. Following the method of Hierarchical, Carousel, and Illichov, to find the traveling wave solution, we reduce to the equation given to the system ordinary different equation. So, for the version of thought of sixth order, the supposition about 4PL periodicity of the solution by y coordinate is taken as simplifying. The solution of 38 by using additional parameters has following form. The version of thought of second order where supposition about periodicity of the x coordinate is taken in simplifying allow the define of the expression for the deflection of surface of the flexural gravity is the form. See Fig 5. Conclusion. Long nonlinear dispersion model that describes flexural gravitational waves propagating in ice cover on surface of the sea is developed by expanding the original three-dimensional problem of hydroelastic oscillation of system elastic plate a layer of an ideal incompressible fluid of various depths in a small parameter. The model takes into account effects of nonlinear fluid dispersion, as well inertia, elasticity, and geometrically nonlinear plate deflection. Proceeding from received equations, they were built of hierarchical sequence of more simple models, generalizing equations Peregrine, Boussinesque, and Korteweg-de-Vries, known from surface waves theories for case of flexural-gravitational waves. For a special case, generalized Korteweg-de-Vries equation, analytic solution, describing propagation of solitons and cnoidal waves in the sea covered with continuous ice were built and analyzed. It is shown that flexural gravitational waves possess some mirrored properties as compared to long nonlinear water waves. As to soliton, this means that without changing the form or dispersion propagates, not a hump as in the clean water case, and speed of its propagation decreases with increases the amplitude rather than increases. In addition, the characteristics of the flexural gravity waves are determined by the wave amplitude and dispersion of plate flexural rigidity and don't depend on the water dispersion and inertial properties of ice cover. There are determined areas of task parameters changing where various types of soliton-like decision for given equation may exist. In similar setting, generalized Kadomtsev type equation, modeling the propagation of long nonlinear two-dimensional flexural gravity waves in the sea covered with continuous ice, has been derived. Assuming periodicity for transverse coordinate, an analytic solution for the equation received has been built in the form of wave packet. Relation among character parameters of the task which provide the existence of such a solution very defined. Thank you for your attention.
Thank you. Okay, are there any questions? Okay, if I have a couple of comments, can you hear me, Vitaliy?
Yes, некоторые комментарии.
Okay,
Excuse me, please. You see that we have problem with English, so I try to translate. Let me.
Okay, first comment, there's a paper, I think 2005 by Chia and Shen, and they do a shallow water equation where they add flexural terms. Are you familiar with that paper?
Excuse me, please. I haven't understood. If you can more slowly, excuse me, please.
Okay, no problem. So okay, yes. So we have a interpreter here. You know, Pavel is going to do the job. So I'm talking about the 2005 paper by Chia and Shen.
Они спрашивают про работу 2005 года. Who is authors again?
Chia and Shen.
Chia and Chen on
That's shallow water plus flexural terms.
Так что это мелкая вода с вот этими flexural, темными гибкими членами, которые вы используете. Знаете ли вы про эту работу?
Ну, в общем, да.
Да.
Посмотрели.
Yes,
we know.
Okay. So I mean, you're going one step beyond here to add also, so to say, gravity dispersion.
Gravity. I don't understand, excuse me.
Так что вы сделали еще один шаг, добавив гравитационную дисперсию из-за гравитации.
Ну,
Нет,
дисперсию гравитационную, ну, и дисперсию ледяной пластины добавили. А там, ну, я не помню, там нету
Значит,
такой. Там нет.
подождите, Виталий Васильевич, вы смотрели эту работу?
Я не помню ее.
Я тоже ее не помню. Значит, речь идет о дисперсии за счет геометрически нелинейного прогиба пластины. Учет нашей модели.
Это геометрически нелинейный прогиб. Обычный прогиб не проходит, решения не существует.
Вы расскажите мне, пожалуйста, что ответить, что перевести.
Значит, вопрос... Что?
Что мне перевести на английский тогда?
Я не
помню этой работы Ченко, поэтому не знаю, на какой, что они именно учитывали, потому что у нас это сделано намного раньше. Это еще 99-й год, а дальше все это просто развивалось, и эти уравнения были получены значительно раньше.
Okay, let me translate. Basically, claim that this current work was made much early in 1999, and he does not remember details of this 2005 work, exactly what was so.
Sorry, I don't want to hold everybody up. I have one more comment, if you don't mind. So I just the final comment here is I think one should be careful by doing long wave expansion for flexural waves because those are actually shorter than the long wave expansion allows.
Translate, please, if it's possible.
Translate, please.
Okay, so I should translate to Russian. Sorry, I started. Ну, в общем, они говорят, что нужно аккуратно делать это приближение мелкой воды, поскольку там имеются волны, которые недостаточно длинные, по его утверждению.
Ага, я понял.
Стоксовские волны, то есть недостаточно и длинные. Нет, это приближение, оно здесь как раз и выделены физические все соотношения. Вот там формула, сейчас я покажу.
Okay, so he wants to show formula telling that it's, you know, it's long enough. So it's basically you claim that there are some effects from finite depth. Is that understood correctly?
Yeah, because the flexural waves are short, so long wave assumption. I mean,
yeah, it was actually also my concern when I heard this talk, but I'm not really expert in this field at all. But you're integrating over volume. But anyway, you want to show, вы хотите показать формулу какую-то?
Да, вот эта формула определяет область соотношения между физическими параметрами задачи, при которых существует это решение.
So this
солитон туда.
This equation shows condition under which we have the solution, soliton solution.
И это физические значения параметра, это не предположение.
And this is physical parameter, not assumption. It's really physical parameter.
Okay, good. Thank you very much. And I assume there are no other questions. Or thanks. Let's thank the speaker again.
Thank you.
Yeah. Okay, very good. Thank you, Vitaliy. Let's go for the photo shoot, guys. Okay.
Okay.
Yep. Could you, Vitaliy, can you stop screen sharing?
Не знаю, может перевести еще раз, потому что...
Oh, it's inside, sorry.